Good morning and welcome to this webinar on the life cycle of a district heating grid. We are two companies behind this webcast. It's Vitek Energy from Sweden and Comsoft NV from Belgium. We are two software companies that provide planning and optimization tools for district heating, and together we cover the whole life cycle of a heating grid. So my name is Johan Helén. And I'm the head of market growth and UX at Vitek Energy, and today I will be your host for this webinar. Together with me I have two speakers. I have Kurt Marlijn, head of innovations from Comsoft in Belgium, and I have Johan Dyrlin, product owner at Vitek Energy located in Sweden. If you have any questions for this webinar, up in your right hand corner you will find the GoToWebinar application and different tabs. You have one that's named questions. If you have any questions, you can feel free to type them in there. They will be private to us as organizers, and in the end we will be able to answer them. So after the two presentations that will be kept by Comsoft and Vitek, we will have a questioning session and we will try to answer as many of the questions as we can. The agenda today, as I said, we are two software companies and we are covering the whole life cycle of a heating grid. So it's everything from the very strategic planning. What can we as a city or a technical consultant do with an area that is in need of district heating? It's optimized design. That's where you look a little bit more at the detail. What do we think that we need to start with? And then we will move over to the Vitek NetSim software, where you could look at more detailed design and analysis, where to place pumps, etc. Then we have grid deployment and expansion, and in the end we have operation and maintenance. A little bit of information about the two companies. We will start off with Comsoft. It's a GIS-based design tool. It's in the very early phase of district heating, where you basically do not have a grid. It's a spin-off from the University of Ghent, founded in '98, and they started off with fiber grids, and now they work with heating grids since about 1.5 years back. 40 employees, clients in about 50 countries, and offices in Belgium and Canada. And then for Vitek, we are also a spin-off of a university up in Umeå, the very Nordic part of Sweden. We were founded 34 years ago by two scientists. And today we will talk about one of the solutions that we have that's called NetSim, a grid simulation software, NetSim. And it has been on the market since the 90s in different shapes, names and forms. And we, as our whole business idea, develop and deliver standardized software for industry-specific needs. A little bit about the customers that we have today. Comsoft a little bit on the early stage for some of the logos here at least, and Vitek a little bit more mature grids maybe. But we are covering all over the world basically, but with Europe as our primary target. So let's get started with this webinar. And if you would like to have more information after the webinar, we will have a follow-up email with a recorded webinar and a PowerPoint. You're welcome to visit our homepage. We have YouTube channels, LinkedIn of course, and we will also invite you to future webinars and seminars. And if you like, you could contact me, Johan from Vitek, or Kurt from Comsoft if you would like more personalized information. So with that said, I will move over to our first speaker, Kurt. So if you would like to unmute your microphone.
Okay, good morning, Johan. Thank you very much for the introduction. The audio from my side listening to you was not so very well. I hope this time is better now. I hope everybody can hear me clearly. So let me start now with the first part, so in the strategic planning phase. What does Comsoft do? Comsoft do Well, we have software for the automated planning and design of district heating networks, and our software is GIS integrated. We're using QGIS, but also other tools are supported. For example, ArcGIS is also supported as another GIS tool. So what is the principle? How do we start? We start from the district where you want to deploy your network. Here on the picture we see a small district with about 1,000 buildings. You see the street center lines, and an important input for the network dimensioning is of course the heat demand. We can work with space heating demand separately of the sanitary hot water heating demand. The space heating demand and the sanitary hot water heating demands can be derived, for example, from yearly gas consumptions. But of course, this is very specific to the area, to the location, depending on the age of the buildings, the level of insulation. So that is something that the user of the tool would have to provide specifically for his area. When this information is available, you can provide a set of technical and financial parameters via a graphical user interface to specify how you want to design your network. So we take into account different manufacturers of pipe systems. So we have the catalogs of the big ones, Logstor, Isoplus, Thermaflex, Rehau, and many others can be added there. We take into account exact diameters, insulation parameters, friction factors for the pressure loss calculations. Important parameters as well are supply temperature, return temperature, and the constraints to which you want to design your network. So maximum flow speed, maximum pressure losses can be specified via the graphical user interface. Another aspect, as I mentioned, are the financial parameters. So we have to specify the cost per meter of the pipes, the different pipes ranging from the N20 to the bigger ones, the N300 or even higher. We calculate with standard price per meters, and we use a scaling factor to scale, for example, more difficult streets or more costly streets with the scaling factor to increase the standard price per meter. Scaling factors can be set on street by street level, and this will also be taken into account later on when the algorithms start routing the network, because we will try to optimize the cost by by selecting the most cheapest routes to interconnect all buildings with the sources. So, and the streets with high scaling factor will be avoided as much as possible, while the cheaper routes will be favored during the routing. So what do I mean with routing? Different clusters. Each cluster is a distribution cluster. The different colors and the lines through the streets in an optimized manner. The clusters each have a distribution substation, and those distribution substations and this type of design are then interconnected via a transport network to the source, which is now not visible on this map, but is on the top right of the district. So we have here a transport network and a distribution network. They can both be dimensioned for different supply return temperature, different pressure settings, different type of pipes, etc. They are fully independent of each other. So the clustering, the routing, the pipe sizing is fully automated. Of course, you stay in control, you still have possibilities to fine-tune, to change parameters, to change sizes of clusters, to group in a different fashion, and also the clusters can be manually redrawn if you want to select more or less buildings in a cluster or group them in a different manner. So next to the technical design, we also generate a bill of material with the full overview of all the pipes which are required in the system, service connections, distribution pipelines and transport pipelines, with the exact length and cost per meter for your networks to give you an estimated budget for the network deployment. So this is the principle of the tool, and in the next slides I will show an example case. Here we have the city of Nijmegen in the Netherlands. They currently have a district heating network in the north of the city, and they are now investigating to deploy multiple extensions in the south city. The blue areas are under investigation because they have higher priority, and we're now going to look at this district here, Hengstal, with about 2,400 connections and about 3,700 number of homes. So also here, the space heating peak demands have been derived from the yearly gas consumption on street level. So this is a screenshot here of our software integrated in QGIS. We have the source here in the northern part of the city. In fact, it is a connection to a bigger transport line which is passing there. And all the dots are in fact the endpoints of the pipelines. So what you see now on the screen could be a possible result of a design. We have 14 energy centers of maximum 1 megawatt, and the small red squares here that we see, they are the distribution substations which are then interconnected with the black lines. The black lines are then transport pipelines interconnecting here to the source connection at the north. Automatically generated, clustered based on the technical input parameters, and a design like this can be less than 10 minutes for this size of network. What we see here is the ratio of the length of the different pipes. We have the service connections, we have the transport pipeline, the distribution network with the length. Here we see the division or the distribution of the distribution pipes, the different types and the length of each, which come automatically out of the bill of material. There are different ways for visualization. We have an OpenStreetMap as a backdrop. In this case, we can label the pipelines and look in detail which pipes have been installed or selected for which segment. There's a possibility to visualize a network in Google Earth to give you kind of a first field survey without really going to the location. You can go deeper and zoom into street view, or even further down at street level you can visualize where the pipes would have to be installed for this network. So let's say the first step is a kind of to give you a high level estimate of the cost of your deployment, but you still have the option now to further optimize your design. So if we look at this figure, these are the different steps in the process. So once the result has been completed, you have different ways now to create and compare multiple scenarios. So you can take a step back, you can go back to the input data preparation, change data there, or you can change technical parameters and cost parameters and run multiple simulations for reasons of comparison. If we now apply this principle on the same districts, we're going now to investigate scenarios of lower heat demand compared to the base scenario. So we're going to calculate a few additional scenarios with 10%, 20% or 50% less space heating demand, and look what the effect is on the network cost. So what we see here on the picture is a design with 50% heat demand reduction. And here we have 9 clusters of 1 megawatt instead of the 14 clusters for the base scenario. The clusters are also bigger, of course. When we look to the distribution of the pipelines, we see that there are higher number of smaller diameter pipes and correspondingly fewer few pipes of larger diameters. Of course, there's also a cost reduction. If you look at the cost reduction of the situation where we have a 50% heat demand reduction, it's about 8–9%. So it's not proportional with the heat demand reduction. That can be explained by the fact that the trenching cost is quite dominating here. We have a large network, we have a lot of trenching to do, and if you have to open up the street to install a pipe of 60 centimeter or install a pipe of 40 centimeter, there will of course be a reduction in cost for the material, but the overall cost is highly determined by the installation works, by the civil works, and the cost will be fully dominated by the trenching cost. So that's a bit the conclusion that we can give here. The trenching cost is really the main driver for this type of network deployment. As I mentioned, you can easily create additional multiple scenarios. So in this case, let's say 50 to 20 minutes maximum, depending on the situation. And well, what we'll do next now is we're going to take one of those clusters which have been generated for this area in Nijmegen. As you can see here on the screen, we have one cluster selected, and this cluster will now be further looked at in the VTech NetSim software. So I hand it over now to Johan to import his data in his tool and further have a look at what can be the added value of proceeding now with VTech NetSim. So Johan, back to you now.
Thank you very much.
Yes, thank you, Kurt.
Go over to the other Johan here as well. Can we see your screen now? Yes, we can. So go ahead.
So thank you, Kurt, and thank you, Johan. And now we're back to the VTech side of things. We will be showing some things in our software NetSim. So it's a grid simulation software. And the first step, as Kurt mentioned, is how to import things from ComSoft over to the VTech side. So we start with just getting the data over from one side to the other. And as we said, we will be working with one of these districts. It's of course possible to import grid as well with all the different sections. But for this session, we will look at one of these sections to make it a bit easier to get an overview of what's happening. So for the import, there are shapefiles exported from the ComSoft side of things, and this is also what we will be using on the NetSim side to import things. So we'll use these shapefiles generated by ComSoft Heat of the grid to import these pipes into our software of NetSim. And we can also import the consumption data from this side. And we have a pretty easy interface for this. We can do this either you can do it yourself as a client, or you can ask us to do this import for you, depending on what you prefer. After the import is done, we have a few settings we need to do on the NetSim side. So we get the pipes and we get the heating demands in from ComSoft. But we need to set up our production plant, and in this case, this is the energy center from this cluster. And we also need to specify the temperatures, the supply temperature, and either a return temperature or a cooling delta T on these nodes. We also need to have a pressure maintenance because we need to know the pressures in our grid, both the static pressure and the differential pressure, so we know what we are working with. And when we have done this, we are ready for calculations on our side. So it's a very fast way to get from one software to the other. So now we will continue on to the detailed design and analysis of the system. And we'll start with looking just at the interface for NetSim. So this is the interface where you can change things on our side. So here we get the data from ComSoft Heat. Everything is input here, and we can now change things on our side if we want to. So if you want to change the heat loads, or if you want to change the size of some pipe or so on to see what will happen, you can do it. You can also easily draw pipes manually in NetSim. So if you want to add some pipes to see what would happen if it was either drawn in a different way, or just to see if you can add some extra consumption at a later stage, it's really easy to do that as well. after we have done this setup, we can continue to some analyzing of the results. And these analysis can be done in a few different ways. We'll start with the graphical one. So in this case, you see the same grid again. And in this case, we have colored it with pressure differences. You can also see the color scale here. So we have red colors for high pressure difference and blue color for low pressure difference. Then we have a scale in between those. This can also be changed, the colors. So if you want to show something else, you can do that to show either pressure, temperatures, flows, or a lot of other factors if you would like to have a look at that instead. You can also see that we have some labels here. In this case, I have the lowest differential pressure point marked, and I also have the production with some information here. And this is something you're in control over, what you want to show. In this case, I've selected to show the pressures in both supply and the pressure difference, and then temperatures in supply and return, flow, and power. There are a few other factors you can add in as well, and you can also remove these if you don't want to have it visible as this. We can also choose to show the flow direction. In this case, there are no loops in this grid, so it will not be too interesting, but if you have a more complicated grid with some loops, the flow direction can be of interest. So we'll have just arrows showing the direction that the water is taking through the grid. Another example of this is coloration on pressure losses. So I just want to show a bit of a different case with visualization. And in this case, we have the colors are for pressure loss per meter. So the red pipes have a high pressure loss per meter, and then we have blue pipes with a low one. So again, we see the colors up in the right corner here, what they represent. And I also have a different set of labels. In this case, I have them on the pipes instead of on the nodes as I had before. So instead of having the production plant, I have the pipe going out from the production. So we can see the diameter of the pipe. We can see how much we lose in pressure per meter, the speed and the flow of this water. And again, this is something you can choose to add or remove information. So you only see what you're in for each specific case. We can also show pressure graphs of our grid. To do this, we need to select a route, so basically specify which part of the grid we want to see this pressure graph for. And these graphs can show pressure, as we see here. We have a pressure. We can also show temperatures if we want to. And this includes height changes. We can choose to show pressure in two different ways. Right now we choose to show the pressure losses basically, not including the height in these pressures, but we can also choose to show the absolute pressure to include the heights in this. So it's up to you what you want to see. This is a more traditional pressure graph. And we can also see that we can have the height changes included here. So we see how the height changes throughout our grid. And we can also show cavitational pressure. So if you want to make sure you're not close to any cavitation in some pipes, you can choose to include the graph for that in here as well. And you also get all the information in tables. If you prefer to work with numbers instead of visuals or graphics, that's fine. All our results in numbers as well. So you can see all the information here. You can sort and filter in our system. So sorting on what you want or filter it. We also have a connection to the map, so you can right-click in our tables to find that point in the map, so it will mark it and zoom into it in the map. And also when you're in the map, you can do the same thing, select an object in the map to get it marked in the table, so you can find all the information you want about it in table form as well. We also have easy copy and paste from this to Excel or other features if you want to continue working with the results in some way, or if you want to make extra more graphs or other functions on this. You can easily copy and paste it to any software of your choice. And then we're back to the design phase, and what I want to say here is basically that we can adapt to the results. So after you've made the calculation, you can of course go back and change things in your grid. So let's say that we thought that our pressure in this part was a bit low. In this case, we could have added a pump, make a new calculation and see what would happen. And you can also make other changes such as changing the pipe sizes, changing consumption and so on. And you can calculate this again and get the new results and compare them. And this is of course an iterative process. You can do it as many times as you want and need to see how the changes impact what you want and what you need to do to get to the end result you are looking for. So now we'll move on to the next part, and I have clumped together a bit the grid deployment and expansion and operation and maintenance of a grid. So what will happen basically when we are done with the design and the grid is actually starting to form or is actually in place. So what we want to do is first is update values to represent our reality. So when we go from ComSoft, we get some values which are either measured or guessed or estimated. So we get some rough values of what's going on, but when we actually deploy our grid, we usually get a bit of a different set of numbers. So in this case, as you see, the power has changed a bit, but also the return temperature has changed. And in the case we're talking about actually measure the power, so maybe it will not change so much, but the return temperature we actually don't know how it will work out until we have the grid in place. So we can easily update this to represent the reality we have. So we can import data. We can either import from building systems to just update the consumption and the return temperatures, but we can of course also import GIS data if you want to. So let's say you actually build the design from ComSoft. The pipes might not be in the actual exactly the same places, so you might want to have the data included. Or if you're not coming from ComSoft, if you already have a grid that is deployed, we can also work from GIS data to set up the grid. And in this example, we have gone from the planned operation to the real operation. And what I'm showing here on the coloration is the return temperature. So we have a pretty evenly distributed return temperatures here. We have some slight differentiations, but it's mainly in because the supply temperature gets a bit cooler as we get further out into the grid. But in the real operations here, you can see more differentiation in color. We have some red pipes, some blue pipes, and this represents the consumers that will have a higher or lower return temperature when you actually deploy the grid. We can also see that we have a bit of a different power in this case so we have a bit of roughly 100 kilowatts extra of power in the real case, just as an example for what could happen between a planning phase and the operation of the grid. And we can also work with different load cases. So what we've been doing so far is working with peak loads, and then we can of course change this to work with other loads as well. And we can evaluate operating condition for different things. And this, for example, would let us see what will happen with the grid in the summer, to see how should we operate the pumps, what temperatures should we use, and so on, to get a good working condition during the summer as well, or other lower load case scenarios. And NetSim also lets you change fast between these load cases. We can adapt to changes according to outdoor temperature. So we can set, for example, fixed supply temperatures that are dependent on the outdoor temperature. Both the return temperature and the heat load of each consumer can be connected to the outdoor temperature. So you can either group them to easily change all at once, or you can change them individually if you have different ways they react to change temperatures. And in the end, we have some time series calculations as well. and this is something you can do in NetSim as well to see how your grid reacts with changes over time. So what you can do with this is specify social loads. And this is an example I have here on the left where we have the power factor. So this is how much of our connected power we'll use at different hours. And this is a pretty standard way it looks during a typical 24-hour period of a weekday. So we have really low loads here in the early morning with high loads when we get to the time when people actually get up and get to work. Bit of a lower load for a while, and then another top when we get to the end of the day and people get home, and then we're dropping down again for the evening and night. So you can specify this. You can also see how temperature changes will impact things. If you change the supply temperature, what will happen in your grid? Either if you increase it, how long will it take for it to have an impact, and how, what happens during the transition from one supply temperature to another. Also, if you have some problems and getting cold water into the grid, how will it spread through the grid, and how long does it take to recover from that? We also can see the travel time in the grid. So if you send out some temperature from the plant, how long will it take to reach the different consumers, and when will it impact them? So I have a test case here where we have the social loads. So I have a little video. And in this case, we are looking at the differential pressures again. So I will just start this video, and as you can see in the top left here, we have the time, and we can see we have a fixed pressure out from the plant. So the red spreads further during the night, and then as we get to the morning, you can see that the blue side gets much bigger as we have an increased heat load. We need to push out more water. So it changes, and then we go back again to the night to have the red part spread a bit further. Yeah, we have the afternoon first, where we have another backing off period, and then going back into the night with pressure difference spreading out further through the grid. So this is something you can see on how the grid adapts to changes over time, and this is usually used for shorter periods from maybe a few hours up until a couple of weeks or so, where you can see the changes that the grid does throughout as you change the loads or the temperatures. And that's it from me. I'm handing it back to our presenter today, to Johan.